Okay, thank you very much. First of all, thank for you for inviting me. Thank Abishka, my friend. We also collaborating. I think the topic that I'm going to talk about it is very, very interesting. During my postdoc, I lived with biology, and I understand actually the concept and the mind of biology, how they think. Actually, I remember the first talk that I gave about data analysis. I presented only the performance and the accuracy, and the question came from my professor, from my boss there during my postdoc, Professor Louise Shaw. She said, where's the genes? Then I start to look to everything different. During my talk with biology, I start to think in different ways. So this actually, I'm going to present part of my projects. Actually, I have three topics that I'm dealing with, which is gene expression. The second one is microRNA, where also I did a lot of work there. The third one is text mining. During this talk, I'm going to just talk about the biological domain knowledge-based feature selection applied in gene expression data. So what happened in this field when the bioinformatics start to show up and the emerging data from the biology become large and big? So most of the people start to use and borrow this algorithm, machine learning, and the feature selection algorithm from the domain of computer science, statistics, whatever. So then I start to think that we need to suggest additional algorithm that can integrate, not just borrow the algorithm and apply it. We need to integrate this knowledge, biological knowledge, into the algorithm in order to understand and to suggest more significant results in terms of accuracy, performance, and also in terms of the outcome that every biology wants to see is the list of the genes. Okay. So the big picture that I dealt with during my years of research was to deal with microRNA gene identification, microRNA target identification. Here in this two projects, actually I dealt with the sequence analysis. That means how we can discover and predict and distinguish microRNA just using the sequence analysis. As I said, I'm not going to talk about this project here, but it's important to show that I dealt with this, because after that I'm going to integrate this information in my system. And also I did a lot of work in gene expression and text classification. Then I start to think about integration those systems together. There is an additional project also I started with Apishka, is using text topics and tracking the same idea that I'm going to describe today. And I wish that somehow we get some results. So just to give you a brief summary or introduction about machine learning, I assume that some of you or most of you are coming from biology. So machine learning actually is the science of programming computers so they can learn from data. So we need, in order to provide we're supposed to provide our machine, I mean by machine the learning algorithm, with data. Then we need to perform some kind of pre-processing, then convert to structured data, and then feed this nice table that consists from column and rows to the machine learning. And then we have a model that we deploy it in some unseen data. So in general, we have data. We partition the data into training and test data, two parts. And we train the model just seeing the training set. The test set is not involved in any stage of the training part. Otherwise, we will have overfit our model. And then we apply the model in the test set. And then as we are doing in education, we score the model evaluation. We see how many times it say, okay, correct, they classify correctly. For example, say for cancer, and saying for non-cancer, and how many times they make mistakes. According to that, we evaluate our algorithm. So as I said in the beginning from the conference, I would like to suggest to use K9. I just recently moved to using K9. Before that, I was using Java, Perl, Weka, MATLAB. I figured out that K9 is very powerful tool that you can program and perform very, very powerful tools. Most of my my tools is done in K9. So for example, in order to apply machine learning, you need to read data table. You partition the data into training and testing. This node actually partition the data. You specify the amount of training and the amount of the testing. You send the training part to the decision learner, which is the machine learning algorithm, could be random forest, support vector machine, whatever. Then it produces a model. The model is moved to this node. This node actually get the testing data and the score. It's very nice, very simple approach that you can explain it very well to biology. And also to teach this for people that they have no programming background is very useful to deal with and do data analysis. So in general, if we have two class data, for example, patient and control, negative and positive, and we would like to find some hyperplane or any line that can distinguish these two groups. We call this as a classifier or decision boundary that actually separate these two groups and try to minimize the error. For example, you see this is actually misclassified, this one is misclassified, and in general, actually we have a function according to the sign of the function, we can decide in which side you are, patient or control. As I said, or you can just find this one, and actually there is no learning here, because this one actually partition the data randomly, and then you will have very low performance. Or the most simple approach is to use linear discriminant analysis, which actually is a line hyperplan if we're dealing with the data in high dimension. Then actually it's easy to interrupt and to understand the model, which actually consists from weights. And you have the parameter x1 to xn, which is actually the gene expression that you have. The weights actually is the solution that you find during the learning stage. And if you look too deeply, actually all these features with low weight, they consider irrelevant or they contribute less to the model, then that means you can just remove it from your model. And actually, for example, if the weights are 0, that means this specific gene or feature is not so important to create or to build the linear classifier. As I said, features with low weights are weak features, and it's simple for understanding. The most usable and strong algorithm called support vector machine. Actually, I just showing you some equation. Don't be afraid. This is an approach that is used very well in the community of bioinformatics, and actually recently people try to understand the concept or the meaning of this decision tree. So actually, this was a brief introduction about machine learning. So what I'm trying to do, as I said before, when I gave my first data analysis, my boss said, what is the genes? Actually, where is the genes? So if you deal with, for example, of gene expression with 10,000 of genes, then even if you build a classifier using all of these genes, then it's hard to understand the model. And then you would like to build a model consist from, let's say, 5 genes. And these 5 genes will be considered as a biomarker for your, for example, for diagnosis. So in order to do that, we're supposed to perform some kind of feature selection. I just read feature selection is one of the core concepts in machine learning, which hugely impacts the performance of your model. Irrelevant or partially relevant features can negatively impact the model performance. So according to this concept, we suppose to search the features space in order to find the optimal subset that can give you highest performance. So in this matter, there is a lot of approaches and tools that doing feature selection. For example, you can read about, I will not gonna explain all this algorithm, backward elimination, where you start by using the whole features and then you just remove the least significant features that actually improve the performance and so on. And there is what very famous algorithm, actually the first time this algorithm was present is applied in gene expression by Isabella. The algorithm called recursive feature elimination. So I will explain it a little bit because then I will rely in the same concept when I present my project about SVM RCE. So recursive feature elimination, actually you have data, you fit a model, then you perform feature selection, you go again and apply machine learning, and again until you remove or until you end up with a set of genes. For example, you can sit with 1 gene, 2 genes, or 5 genes on 100. This is actually depends in the performance you would like to end up. So the algorithm is actually compute an importance score for each feature. Actually, if we are talking about linear, then actually the importance is the weight of the features. For example, weights with 0, that means the corresponding feature is not so important, then you can just eliminate it. So at the least important features are then removed. For example, you can remove feature 1 by 1, or you can remove 10% or 50%, and then you go again and fit again the model and remove again and again, because that is called recursive feature elimination, because you apply this approach recursive way. Okay, so the gene expression, I assume that everybody here is hear about it. Actually, it's measure the expression pattern of many genes at once. So in the end, we have this nice data that consists from 2 groups or 2 classes. And again, it could be unbalanced data. This is something very famous in this data. For example, you have the column represent the patient, and the rows represent each gene, and the value here is represent actually the expression of these genes over this sample. The numbers here has no meaning, but the ratio or the relative values of this number, they have the meaning. For example, if you have these genes, for example, is expressed 0 here and very high in this healthy, that means this gene could be biomarker or the opposite direction. I see chat. Okay. So during my postdoc, I dealt with a lot of data analysis. And during that time, when I have the interaction with the biology, I start to look to the data in different ways. So when I provide, actually, this is something funny. When I present then my boss said, where's the genes? And I have here non-smoker. I will tell you the story. So then actually I changed the model. I start to give her the rank of the genes. And then we took these genes and moved to David to find the relation between these genes. I said, okay, instead of doing that, let's start to impede this information into the algorithm, because we know that correlated genes, they have the same function. So if the correlated genes have the same function, so let's put it together and start to rank it together. So put the similarity guys together and just deal with them together. Then actually the first idea that came is called recursive cluster elimination, which is actually associated with recursive feature elimination. And I start to deal with this project. Maybe I will answer the question later. Okay. So during the data analysis process, we're doing a lot of procedure, a lot of work. First of all, we do pre-processing to prepare the data to be ready for machine learning or for analysis. And there is the couple of approaches that you can perform. You can perform PDA, PAM, LDA, RFE, you can cluster the data. There is a lot of approaches and algorithms that can apply in this data. In the end, you would like to see a heat map that tell you these genes are very low in this NH, non-healthy, and they are somehow high in the other group, or something like that. Then actually we assume and we say this is the biomarker. According to the gene expression, we can just distinguish the two groups. So the question is, in machine learning, how we can take this huge data, I mean huge or big data in terms of number of genes, 30,000 genes or more, and then end up with something like that. Also, we would like to, during the data analysis, we try to find maybe the number of genes, over 10 genes, 20 genes, 100, and then we can say, okay, for my model, I would like to take this performance. So I will have 95% true positive, true negative, and average accuracy. Always we run the model 1,000 round or 100, and as you said, we can also, as I said before, we can give a score for each sample and then also plot this score to see the difference between these two groups. And also we can plot the data using PCA, multidimensional scaling, to see how the data is behaving according to top 200 genes. So actually this picture gave you information about, visual information about your data. Okay. So now I will start to explain the merit or the generic approach that I have been developing with collaboration since 2007, I think. Yes, or 6. So actually, if we have data that consists from two classes, even with one class we can deal, but let's assume for simplicity that the data consists from two classes. The two class is two label, healthy, non-healthy, and is gene expression. So, and we assume that we have a grouping function, general grouping function. Now I'm talking about general grouping function. I will start to explain one by one. Then, for example, the grouping function could be clustering, to cluster the genes, not the sample. Could be microRNA target, could be kick pathway, could disease. That means a grouping function could be any biological function that you would like, that you can use it in order to put the genes together. Okay, then we have list of genes. Then G, you apply G, grouping component, that actually create a list of groups like this. So one group is actually consists from different or a set of genes. These genes, they are sharing some similarity. So in the end, we will have a set of gene groups like this. Then the question, how we can rank or predict if this group can distinguish the data that we have. Then actually we perform the ranking component. So ranking component could be, you can actually here and here you can put any idea that you would like. So the grouping component could be something that you would like to use biological information. And the ranking could be any approach that you would like. We decide to use the machine learning to split again the training data into, for example, cross-validation using support vector machine or random forest or whatever. But we present the data just according to this group. That means now we examine each group individually. We represent the two class, which is the training data, just according to the genes that belongs to this group number one. That means now our data just consists from these groups, these genes. Then we apply sort of machine learning in order to predict or to give a score or a rank saying these genes belongs to group number one, can distinguish the training data, for example, 90% accuracy. And then actually we give a score for each group. Then we can build a classifier from the top first group or the first 1 and 2. and the first one and the three and such on. We choose to try it until 10. Then we apply the model in each group, the top group. We end the test data. Again, we always partition the data into training testing. All this process is happening just on the training data. We apply then the test part to see if we get some sort of good performance. This is the algorithm that we developed for ranking. So the ranking algorithm actually we call it R. You get X as a sub data. M is the group. F and R are the how many times you would like to perform cross-validation or another sort of performance measurement. So then we actually go over each group. We remove all the genes from XT and XV, which are not in the group MI. That means the data now represented just by the genes belong to the specific group. And then we perform train classifier, for example, support vector machine, or as I said, another algorithm. Then we calculate and we give a score. So the score is saying this group alone, for example, group number 2, can distinguish the data, training data by 90%. So the 90%, 0.9 is the score that given to this group. Okay. So since 2007, actually, I started to develop with my colleague algorithm that we called SVMRC, support vector machine recursive cluster elimination. Then we apply the same approach, SVM RNE, recursive network elimination. Then I start to apply RCE, recursive cluster elimination with ensemble cluster. Here, actually, we cluster the data in different way. This actually was work with Dr. Loai, where he actually is expert in ensemble clustering. Then we just cluster the data in different way. In 2019, we start to work actually in combining microRNA with gene expression. Recently, we have updated SVMRCE, and we add more functionality, and we also apply it in K9. There is the two running project now. Cognate, actually Cognate is now is under review, where actually we use Pathfind R, I will explain it later, to produce the significant enrichment pathway. Then we rank each pathway the same way that we have done before. And also, just recently, we solved, I think, a very interesting approach where we have not the gene expression. All these tools actually deal with gene expression. This one actually deal with gene expression and the data from MERTAR base in order to group the genes. But this tool actually take as input microRNA gene expression and also the gene expression. Then the question is how we can combine and integrate these two data to figure out some useful information in terms of microRNA and target and gene expression. This one is actually is running project. We almost done. All the workflow is ready. I will be happy to discuss collaboration. And also this one is, as I said, is under review. So I go back to the first idea that we have applied. So we have data. We split the data into training testing. Let's assume 90%, 10%. Then we apply k-means in order to cluster the data. Now we have n clusters. According to k-means, we use the correlation matrix. That means these clusters contains genes that are correlated according to applying the k-means algorithm. K-means algorithm actually is a clustering algorithm. Then we have a set of clusters that k-means output. Then the question is how we can score it. Then the second approach is, the second component is the scoring or ranking. As I said before, according to this generic approach. We perform a kind of cross-validation, internal cross-validation on the training part when we apply it in each clusters. Then we give for each cluster a score saying if these clusters can distinguish the data very well. We sort it, we remove 10%, then we go back again and we cluster again. Then we process the approach again. We remove lower clusters. In this approach, we don't remove as VMRFE couple of genes. We remove clusters together. So the weak clusters is removed. Actually, the question here, we dealt with individual cluster alone. The question that also we would like to explore, this is another project that also I have a student in Abdullah Gul, that he's supposed to start this project, is what about considering different combination of clusters? That means we don't need to in this approach, we consider individual cluster alone. But what if we cluster number one, cluster number two, if we merge it together, we will have a higher performance. So in this way, we're losing some information. So actually, there is an idea and a running project that we as I said, with Abdullah Gul University, that we try to find the optimal combination of these clusters that can improve the performance of this approach. Then actually we move to SVM-RNA, where we cluster the data, not using k-means. There is a tool called GXNA that actually using the gene expression in order to suggest network between these genes. Then the network actually is a groups for me, like this, groups. So again, here the groups are clusters, here the group are actually the network. Again, we do perform similar approach, and we redo that approach again and again. This two paper was published in PMC Bioinformatics. This one actually is the way how we can actually cluster the data in different way, what we call it ensemble clusters. I will not go deeply. The paper is ready to read, is published. This was collaboration with Dr. Lai. Recently, I did also this project with Professor Jens Almers, also a keynote maybe tomorrow, where we integrate information from microRNA and gene expression. This paper actually published in Bioinformatics Oxford Journal. This too, as I said, is just under consideration. This one is a running project. Okay. So if we have data, we apply G, the grouping, and we apply R in order to clusters. This is the concept that we did it. And also then we compare our approach as SVM-RCE with SVM-RFE, with PDRFE. This paper, as I said, is published in BMC Bioinformatics. The output of our approach is consist from two parts, actually the number of clusters and the number of genes in these clusters. To match it, we look to SVM-RFE, we match 11 with 12, and we apply the output here. And we see in some cases we are outperform RFE, even in most of the cases here. This one actually we did bad, but the RFE did much better from us. So what is he saying here is not just only the significant list that we have, also the heat map, how it's looking. If you look here, you see we have clusters. We capture the clusters of genes that they are have some similarity. But here actually, if I will not go deep with the difference between SVM-RFE and SVM-RC, you are invited to read this paper. But actually we capture a cluster of genes rather than dealing with gene once at a time. As I said just recently, we submitted this project when I was visiting during the summer in the previous year with Star Institute. We convert the project SVM-RC into K9. But additionally, we add a ranking. We add what we call it ranking ranking function. So the traditional rank was using the accuracy, but during this version, actually, during this update, we let the user to specify the weight of the different measurement that we can calculate from our performance. For example, accuracy, sensitivity, specificity, F1, area under curve, precision. For example, for instance, you might be interested to have higher sensitivity, and you prefer to have higher sensitivity rather than higher specificity. So you will give a high weight to sensitivity and lower weight to specificity. And we try to different rank approach function. And actually, we see that different rank function can improve the performance even dramatically, like even 16% in some of the cases. As I said, the approach is also the K9 workflow also accessible. You can download it from my homepage or send the email. I can send it to you. The next actually question is to find the optimal weights that can give me the optimal performance. This is another project that is actually open for collaboration. Okay, 2009, actually, we wrote that as a conclusion in our papers as RCE, is that we suggest that gene interaction network or other biologically relevant matrix that group the genes based on functional parameter might also be useful. According to that, actually, we run this approach. We use GXNA. That is a tool that can take as input gene expression and plot or create the networks. Now the networks, as I said, is groups, and then we rank each network individually. Again, we published this in BMC Bioinformatics. This work was a collaboration with Professor Luis, Professor Larry Minevich from Haifa University, and his student, Muhammad Kittani. Okay, next, the third project in this topic was using ensemble clustering in order to put the genes together, in order to group the genes together. This project was with Luai Abdullah, as we use his approach. Rather than using k-means, we use the ensemble clustering in order to group the genes together. Okay, so then we start a new project where we consider gene expression, microRNA grouping. As I said, I have experience also with microRNA expression and machine learning. These two actually is the last project that we are dealing with now. This microRNA grouping with gene expression, now actually we did this tool. We call it MATI. We publish it in Bioinformatics. Okay. So what is MATI is? MATI is we have as input gene expression, but we don't use about microRNA and its targets. So then we use this information in order to group the genes from this data. What does it mean to group the genes? For each microRNA, there is a set of targets, validated target. So these genes are considered one group that associated with this one microRNA. But for our algorithms, this is one group, and this is the other group, and this is the third group, and so on and so on. So the question, we use this two knowledge, biological knowledge and gene expression, in order to integrate this information, biological information and gene expression information, to put the genes into groups and then perform the two-step component, the grouping using this and the ranking as we have done before. Actually, I remember we had tested here support vector machine and random forest. We found that random forest give us much better results in this term. Okay, the workflow is published we publish it during our publication. Also, it's written in K9. somehow complicated. Recently, we just make it much easier in this way. That means we convert again the K9 into simple way that can be easy for interpretation. And if you look to the workflow, you see you have created the groups. This is meta node. You rank the group, then you run each one to remove the lower clusters, estimate in the test data, performance and test, then you collect the output. Actually, the workflow in K9 somehow describe this algorithm that we describe here, or the main algorithm that we describe here or here. So actually, in this way, it's easy to interact with the biology community and explain the algorithm that we are developing. This is a new version. This is also, we try to develop another stuff with this K9 approaches. We are open also for collaboration. We have different idea to improve and add more component to this workflow. Okay, this is actually the two tables that describe the MAT algorithm. I will not go deeply to that, but you can read it over the manuscript. This is one output of the ranking approach, the ranking component. For example, if you see here, this is the microarray name. This is the accuracy. The accuracy is the rank. And the list is sorted by accuracy. That means all of these actually ignored from our analysis. We consider the top one or top two. And something interesting, you see this is one actually consists from just one gene that belongs to this microarray and still have very good performance just considering this one gene. And this one actually consists from 3 genes. The other project that also I start with the Professor Jens to see the influence of the size of the clusters or of the group. We assume this one is very big, giving higher accuracy from this one because the number of genes involved in this or belongs to this group. We start to deal with that to develop computational ideas. It's just in the first step to find a solution. The idea is to eliminate the size of the group in terms of ranking performance or ranking score. Again, we run it against SVMRC. This is the most similar approach that we have. We've tried to find similar approaches. We don't find anything that can compare to MATI. We compare to SVMRC. We show that we get a very interesting result. But again, the idea here is not to get very high accuracy just, only to suggest different significant list of genes which is associated with microRNA. For example, if now the biology take this list, the top 2, and the top 2 are not, okay, they can distinguish the 2 class with very high performance or accuracy. The thing here that these genes are associated with microRNA. So the approach here actually predict the targets or the target involvement in the data that is under investigation without knowing any information about the gene expression of the microRNA itself. This is the unique of these tools. I suggest to you to read it over bioinformatics. This data actually is not published yet, where we group the genes according to pathway, KIG pathway. Now the grouping function is KIG pathway, or could be also we did some comparison, or another study is to put the genes disease. These two projects we're still also considering, and we think about to make a general approach that the biology or the researcher can decide how to group the together. Okay. The two recent project is the one called Cognet. This project was with Professor Cesar and his student Cesarman and his student Iggy. They published a tool called Pathfind. This tool is R package. When getting input a list of p-value, that this p-value is extracted from gene expression. Then we feed this list to the Pathfind R to find the active subnetwork search and filtering. Then he suggests apply enrichment analysis in order to suggest the significant subnetwork. Okay, when I saw this tool, I have the idea to combine it with the idea of rank and the grouping. So now the grouping is Pathfind R here. And again, we perform similar ranking approach as we have done before, but we don't have recursive because we redo the process, we will have somehow slightly or maybe different, but the similar groups. So we create n data set for each pathway. We rank each pathway, and then we test it in top ranked, maybe 1, 2, 3, and so on. According to that, we can decide to which rank we stop and get the higher performance. As I said, this tool is under revision now. This is the result that we show, compare Cognet using random forest and the SVMRCE with MATI. And we see that Cognet getting very, very good results, even reaching 86% performance over the 13 dataset. This is the average. And the recent project that is still in running, we call it Mere Correlation Net. So this is the first time we feed our model with two kinds of data, the microRNA expression and the gene expression. And then the question, how we can integrate these two kinds of data in order to apply our approach of grouping and ranking. So we group the genes. First of all, we find the differential expressed microRNA. Again, we apply it in the test part. And also the differential expressed genes from the gene expression. Then when we apply correlation between these two matrices, we set a threshold 0.0 minus 0.6. That means we put all the genes that are negatively correlated with this specific microRNA into one group. So we hypothesize that these genes should be somehow related to this microRNA, could be the target, or they have some interaction with this microRNA. Because when this microRNA negatively correlated with these genes, should be some biological information between these two genes and the microRNA. So now we have a groups, we rank it, and we test it. As I said, this is in preparation. And also this project with actually Dr. Borjo from Abdullah Gul University, and Mitra and Christian is from Jefferson University. Actually, they are trying to find the biological validation of our outcome. And actually, Mitra did very nice analysis and find, when considering the top microRNAs, he found a correlation between our prediction and to what is known in the literature in terms of cancer and potentially in terms of cancer types. We still try to understand more deeply the data here and the outcome of the data. And again, we compare it with the MATI, with the Merck. This is our project, and RFE and RFE. This is the most similar approach that we find, and we try to compare it with them. Again, we wrote this in K9. So at the end, I would like to introduce you to my homepage. You can access my homepage and all of these tools. Actually, I'm also modifying this list. as much as I can. And all of these tools can be downloaded, and it's free for your use. You can use it, and if you have any question, I'll be happy to answer and help in using these tools. Thank you for listening. And I would like to mention all our collaboration. Professor Jens, Larry, Mohammed Kittani is a student. Professor Louise, I still collaboration with her. Recently, we start with Rahman, the SVMRCR code, and with Abdullah Gul University. This is my picture when I was young. Dr. Luay Abdullah, we have applied many projects in ensemble clustering. And the Borjo group, Gokhan is responsible about the last project, Mir Core Net. And also Amhar is the guy gonna solve the problem of optimal optimization of the clusters. As I said, we have collaboration with Mitra and her boss to actually to find and to interrupt the outcome of our tool. Ugur and Ige, we did the project of Cognet, and also they published the Pathfinder tools. Thank you very much, and if you have any question, I will be happy to answer.